Hello, welcome to this short primer on our upcoming publication in Science titled Bifurcation of Planetary Building Blocks During Solar System Formation. I am Tim Lichtenberg from the University of Oxford and I'm excited to share the key results of our research with you. We have worked on uncovering the deep past of our own world and how the solar system came into being. To do so, we connected recent findings from astronomy and geochemistry and found an internally consistent scenario that explains many properties of the solar system at present day. The image you see on the screen illustrates some of the central aspects of our work. You are looking at an artistic impression of the solar nebula, a disk of gas and solids that surrounded the young sun at its birth, 4.5 billion years ago. You see the inner terrestrial planets and many smaller building blocks, so-called planetesimals, colliding, accreting pebbles, melting and outgassing due to very high temperatures. A novel insight from our work is that the solar system formed in two distinct episodes. The first of these episodes had already started when the sun was still forming. At that time, the inner terrestrial planets started accreting, here shown in red in the middle of the screen. The second episode started approximately 500,000 years later, when the building blocks of the outer planets formed, shown on the top right of the image in bluish color. Because of the delay in formation time, the outer planets inherited a much smaller amount of radioactive isotopes than the inner planets. The radioactive decay strongly heated the inner planets, but not the outer planets. The inner planets therefore melted, formed iron cores, and lost their initial volatiles, such as water, very quickly. The result of these events is that the inner terrestrial planets today are relatively dry, while the outer ones are rich in volatiles and water. Let me summarize a few key aspects and highlights of our work. We performed computer simulations that show that the formation of the solar system can be explained by the mentioned two-step process. The inner planets started first, but accreted slowly. The outer planets started later, but accreted more rapidly. This is because of the movement of the so-called snow line in the solar accretion disk. The snow line is the location of the gas disk where water ice transitions from being the gas to ice phase. The sequence of astrophysical formation effects and geophysical evolution explains the split in water content of the inner versus the outer solar system and reproduces the formation chronology that is recorded today in meteorites. In particular, it reproduces the time clustering of iron core formation and water rock reactions that we observe in meteorites and the difference in isotope composition of extraterrestrial materials from the inner and outer solar system. In this new theory of solar system formation, the terrestrial planets are dry because of their timing of accretion and the inventory of radioactive isotopes that got incorporated into their earliest building blocks. Specifically, the short-lived radioactive isotope aluminum-26 heated planetesimal interiors on a timescale that is comparable to the timescale of planetary accretion. This is different from the classical scenario of solar system formation, in which the initial building blocks are thought to be formed at roughly the same time in the whole disk. In this classical view, the difference in volatile and water content is usually explained with the static position of the snow line. In contrast, in our new scenario, the snow line movement consistent with astrophysical models is important to trigger planetesimal formation bursts at different times and locations. This new solar system formation scenario gives some insights into the relational place of Earth and the solar system relative to extrasolar planetary systems. Because the inventory of volatile elements in the Earth is a result of the specific chronology and path of accretion, exoplanetary systems should show strong variations in atmospheric and climate state compared to our own world. For example, the Earth is dry because of the inventory of radioactive isotopes in the early solar system, but other planetary systems likely have very different inventories of these radioactive isotopes. And so, the geophysical evolution of planets in these systems takes a different path, resulting in, for us, seemingly exotic compositions and climates. Our work has has many more interesting implications, but I will finish this brief presentation here with the contact details of our international author team. We are happy to talk to you about this research, and thank you very much for your attention.